Good morning. This is Dr. Jingbo Louise Liu from Texas A&M University, Kingsville. Today, I'm going to discuss with you about the chapter 6 related to addition reactions of alkene. Before we learned about preparation of alkene from different types of compounds, today we are going to learn about the alkene reactions. Essentially, the alkene reactions can be classified into three types of reactions. The first one is called addition reaction to the double bonds. The second type of reaction called oxidation reaction. You want to break up these carbon double bonds. The third reaction, we are going to consider it polymerization reaction. Today, we are going to show you another different rule called Markov-Nikov's rule. Similarly, we are going to show you anti-Markov-Nikov's rule. That's the major points for today's lecture, addition reaction of alkene, but also we are going to discussing oxidation reaction and the polymerization reaction. So let's move on to the first topic, alkene addition reaction. So we are going to discussing hydrogenation reaction. Just imagine you have an isolene. You have a carbon-carbon double bond, and there is a pi bond, meaning this carbon-carbon is considered the functional group. The chemical reactive sites will be located between these two carbons, which composed of a pi bond. If you're adding the hydrogen molecules between hydrogen atoms, you are going to form a sigma bond. Under the catalyst, particularly the different metals, so you are going to add one hydrogen to one of the double bonded carbon, another hydrogen atom to another double bonded carbon. So this chemical reaction is called hydrogenation reaction. The hydrogenation reaction of alkene is an exothermic reaction, meaning the heat will be given off from your system to the surroundings. This reaction, you can see, has a delta H, which is a negative 136 kilojoules per mole. So this reaction was found to have very high activation energy. Therefore, normally your catalyst is required to enhance this chemical reaction. So the chemical reaction has another very important nature. It's called stereoselective reaction. Stereochemistry of alkene hydrogenation tells you the alkene with a planar structure is going to subject to two different types of addition. Can be thin addition. The thin addition can be also anti-addition. In the case of hydrogenation reaction, the thin addition will be happening, meaning two hydrogen atoms will be added to the double bonded carbons from the same side. On the other hand, if you are studying about halogenations such as bromination or chlorination, you are going to find the anti-addition, meaning two Cls or two chlorine, two bromine atoms going to be added to double bonded carbon from the opposite positions. You may have a question, why is this? Therefore, we need to understand the mechanism of hydrogenation reaction. So there are totally 4 different steps of hydrogenation reactions. The first step is called hydrogen atoms bound to the catalyst surface. So this colored, you see this spherical part, they are representing the catalyst surface. So hydrogen atoms are going to be bonded to the catalyst surface, your first step. And you also have your alkene or alkene such as isolene. You have your alkene. This alkene, you have that double bond. That double bonded carbons going to be attracted by the surface of your catalyst. That's your second step, followed by your first hydrogen atom. Your hydrogen atom is going to be attracted or transferred from your catalyst surface to your alkene double bonded one of the double bonded carbon. That's your third step. One of the hydrogen atom is going to be transferred from your catalyst surface, such as from the catalyst surface, to one of the double bonded carbon. You form a hydrogen carbon single bond. The very last step, number 4 step, so your second hydrogen atom is going to be transferred to the second double bonded carbon. In this case, you are going to form an alkane. So this alkane leaving from the surface of your catalyst. There's 4 major steps of your hydrogenation. So in this case, you can see due to the surface attraction, so the hydrogen atoms, they are going to be bonded to the carbon double bonds from the same side. You call it a syn addition. And then you may have another question: which kind of alkene has the highest reaction rate? You're also going to use the heat of hydrogenation to measure it. If the heat of hydrogenation, this is very high, if this is very high, the related molecule is not stable. On the other hand, if it's very low, if let's say the molecule has a lower heat of hydrogenation, so that reactivity will be enhanced. In other words, the final product will be more stabilized, meaning if you have more substituted alkene, that substituted alkene molecule will be more stable, meaning the hydrogenation heat, the heat of hydrogenation of that associated substituents will be essentially lower. So such as trans 2-butene has the heat of hydrogenation in 115 kilojoules per mole. The other one, the 1-butene, so it's 120 kilojoules per mole. So in this case, this molecule is going to be subject to the mole reaction rate. So that's how you are going to use the heat of hydrogenation to determine the chemical reactivity and the associated stability. The stability is corresponding to the lower heat of hydrogenation. And then this addition reaction can be subject to a different approach. If you're adding hydrogen halides into the alkene, this reaction is called halogenation reaction to the alkene. You have your carbon-carbon double bond, and you have a hydrogen halides. The hydrogen halides composed of hydrogen, which is positively partially charged. Your chlorine, which is negatively partially charged. Therefore, you will have a question. So which of the carbons will be bonded with the hydrogen with the positive end? So that's a question. But anyway, hydrogen will be added to one of the double bonded carbon. Chloride or bromide halides will be added to the second double bonded carbon. So therefore, this is called pi bond of your alkene, which has the higher electron distribution or density. So meaning that the carbon-carbon double bond is electron rich. So that part, that double bonded part, this part will be your reactive sites. So that electron-rich region will result in polarized, partially positively charged hydrogen to be connected to the more negative carbons. And then your chloride, which is negative ions, will be connected to the more positively partially charged carbon, which is related to your carbocation. Again, which alkene is more reactive? Essentially, again, you have more substituents, the related molecule will be more stable. If you have a HF, hydrofluoride, hydrogen fluoride, hydrogen chloride, hydrogen bromide, hydrogen iodide, your iodide I is a good leaving group. Therefore, the reaction rate will be hydrogen fluoride, which is much weaker, followed by hydrogen chloride, and hydrogen bromide, hydrogen iodide has the highest reaction rate. So again, what we want to show you, this is your hydrogen highlights. Hydrogen is more partially positively charged. Your chloride in the future or bromide, they are more partially negatively charged. This positive will be attracted by the carbon, which is more positive proton, will be positively charged hydrogen end, will be reacted or bonded with your carbon, which is more negatively charged. And the carbocation end will be more possible to react with your chloride or bromide. Normally, hydrogen halide related to HBr and HCl are commonly used for these hydrogenation reactions. For example, if I have this 1-methyl cyclopentane reacted with your hydrogen chloride at 0 Celsius, what's going to happen? You are going to produce a chloro replaced methyl cyclopentane. You have two possibilities of this two carbon, double bonded carbon, which reacted with HCl. So here this carbon, let me call it carbon 1. This carbon 1 connected to one carbon, second carbon, and you have double bond. This carbon 1 has no more hydrogen which can be connected to it. And the second hydrogen, you have a double bond and connected to another carbon. Therefore, over here, you have one more hydrogen. So where this hydrogen is going to be added to carbon 1 or carbon 2? Research indicated the hydrogen will be added to both possibilities, will be added to possibly to hydrogen 1, to carbon 1 or carbon 2. Which one is your product? So this one we are going to use Markov-Nikov's rule to tell you which of this hydrogen will be added to which of the carbon. So I can tell you this, your hydrogen will be added to the second carbon. So you have a carbon 1, carbon 2. The second carbon has more hydrogen which is bonded to it. Based on Markov-Nikov's rule for addition of hydrogen halide. So you can see this. When an unsymmetrically substituted alkene reacted with hydrogen halide, the hydrogen atom adds to the carbon that has more hydrogen atoms. On the other hand, your halogens will be added to the carbon with fewer hydrogens. In another word, if you have a carbon with more hydrogen, that hydrogen will be added to that carbon. For example, second example, if you have a 2-methyl propene, you have my carbon 1, carbon 2. Carbon 1, you have 2 more hydrogens. When this 2-methyl propene reacted with HBr, where is the hydrogen going to be added to? hydrogen will be added to your first carbon. Your bromide will be added to your second carbon. Therefore, you are going to produce a terbutyl bromide. So carbon 1, 2, 3, 4. You call terbutyl bromide. Again, followed by Markov-Nikov's rule of addition of hydrogen halides. If you don't have light, if you don't have hydrogen peroxides, if you have hydrogen halides, which are going to be added to your alkene under special conditions, such as you are going to use peroxides, and you are going to use light. In that case, you are going to produce an anti-Markov-Nikov's product. So be careful. If you simply react with alkene with halides, you are going to follow Markov-Nikov's rule. So what's the mechanism? So how the reaction is happening? So we can show you. Totally, there are 2 steps. Step 1 is called protonation. Step 2 called combination. If you have this 2-methylpropane, you have your hydrogen bromide. What's going to happen? This pi electron, actually 2 of them, pi electrons, is going to attract to the more positively partially charged proton. So you are going to, this proton has no electrons. Hydrogen and bromide, they are subject to the heterolytic bond cleavage. This bromine, this Br, take these 2 electrons, retain these 2 electrons to form a bromide negatively charged ion. So therefore, hydrogen is going to be connected to your double bonded carbon to form a carbocation, positively charged ion. We already know your tertiary carbocation is more stable. Therefore, you produce a tertiary carbocation cation, and you also produce a chloride or bromide halides, negatively charged. Negative positive charged ions through electrostatic, they are going to attract to each other. So therefore, you are going to combine cation and anion. So positively charged carbocation, negatively charged bromide, they're going to combine. You form a terbutyl bromide. So this is what happening. The first step, protonation. This step is a slow step. Therefore, the protonation is the rate determining step. Your protonation is going to produce or yields the most stable carbocation. If you did not produce the most stable, the methyl or alkyl group or hydride is going to be subject to the shift to produce a more stable carbocation. Therefore, your proton as to the alkene carbon, double bonded carbon, which will initially have the most proton. So the most proton, you're adding 1 more proton, the other carbon will become a carbocation with more stabilized charge. Second step called combination of cation and anion. It's due to your positive negative charged ions, they are easily and rapidly to be combined to form a bromide or chloride. Again, bromide, chlorination or bromination is more hydrobromination. Hydrochlorination is more commonly used reaction for this addition of your alkene. This reaction, you consider it Markov-Nikov's reaction. Follow the Markov-Nikov's rule. So we give you a little bit more example about the carbocation rearrangement. For example, if I have a 3-methyl 1-butane reacted with HCl, So what you want to see, you want your carbocation to be more stabilized. Otherwise, the carbocations will rearrange to form a more stable cation. So the fact that the rearrangement occurs on the addition of hydrogen halides to alkene provides further support for the reaction mechanism. We are going to show you a couple mechanisms. So the example again is your 3-methyl 1-butane. You have two carbons, carbon 1, carbon 2, which double bonded. Carbon 1, you have two hydrogens. Carbon 2, you have only one more hydrogen. Therefore, the chlorine theoretically should added to the second carbon. So you should receive this molecule only. However, in our real product, you are going to see the chlorine added to this third carbon more than the second. So this reaction, so 2-methyl 2-chlorobutane was found to have 60%. What happened? Let's take a look of the mechanism. So the mechanism can help you to understand why you form two different products. So let's see. First step, protonation. Protonation meaning this pi electrons from your alkene is going to attract it to the hydrogen halides, to the hydrogen, and the hydrogen halide, that single bond, sigma bond, is going to subject to the hydrolytic bond cleavage. Therefore, you produce a chloride, and hydrogen will be bonded with this carbon, and then you form a secondary carbocation. Secondary carbocation is less stable. What's going to happen in this third carbon, pink colored hydrogen? This hydrogen is going to shift, called hydride shift. Hydrogen take 2 electrons, so form a 3-numbered ring, which is your intermediate, and then this carbon and the hydrogen bond will be break up. You produce a tertiary carbocation. This tertiary carbocation is more stable, meaning this chloride is going to attract it to this tertiary carbocation to form this we call the 2-chloro-2-methylbutane. So again, you need to double check which carbocation is more stable. So the related highlights possibly is your predominant product. So the product yield possibly higher. That's how you are going to determine it. So what's the mechanism of this reaction? Again, mechanism related to protonation and to recombination or combination of cation and anion, possibly suffered or subject to the carbocation arrangement in order to produce or in order to form more stable carbocations. So that's about your hydrohalogenation reaction. You already learned the hydration reaction is the called syn addition. So you use that catalyst 4 steps. You have your hydrohalogenation. You may go through 3 steps. First one is called protonation. Second one called the combination of cation and anion. The third possibility may be related to the carbocation rearrangement. So if you have alkene and you're adding water into the system, what's going to happen? You are going to have something we call the hydration reaction. This hydration reaction, you need to know 3 key parts. Number 1, this hydration reaction is also called the electrophilic addition of water. Number 1. Number 2, this reaction must be catalyzed by using strong acid such as sulfuric acid. This reaction, number 3, this reaction is also follow the Markov-Nikolov rule. So first of all, you need the addition reaction called hydration reaction is also called electrophilic addition of water to alkene. And this hydration of alkene is catalyzed by strong acid. And this hydration of alkene follow the Markov-Nikov's rule. Also, about your reaction rate, you follow the same way. The more substituted, so the related product will be more. The reaction rate of the hydration will be faster. So what's the mechanism? So you can consider 3 steps. So this reaction sounds like your alcohol elimination reaction, but in a reverse direction. Your dehydration and hydration reaction, they are usually in equilibrium. Which direction is more favorable based on essentially the water? So you consider this H2O as your external stress. Let's come back to the mechanism of your hydration reaction. Again, we are following the Markov-Nikov's rule. Markov-Nikov's rule states the proton is added into the alkene carbon with the most hydrogen atoms. If the carbon has more hydrogens, you're adding your hydrogen to that carbon. For example, if I have my 2-methylpropene, so of carbon 1 you have 2 more hydrogens, carbon 2 you have no more hydrogen. Therefore, hydrogen will be added to this first carbon. Your OH will be added to the second carbon. The first step you call the protonation. The second step we call it nucleophilic addition. Of what? We're going to show you. The third step called deprotonation. So you are going to produce a terbutyl alcohol. Again, the alcohol is going to be added to this second carbon. First step called protonation. Protonation meaning in your strong acid you have your hydronium. Hydronium, oxygen, and hydrogen bond is going to subject to the hydrolytic bond cleavage. So your carbon double bond, that pi electrons, is going to attracted to the hydrogen. Therefore, the hydrogen is going to be leaving as a proton to be bonded with this carbon. And then you form a tertiary carbocation. This part of carbon becomes positively charged. Because you lose a proton, this hydronium becomes a water molecule with 2 electron lone pairs in your oxygen p orbitals. Second step, due to the formation of this carbocation, you are going to see positive charge ion and the electron lone pair. They are going to attracted to each other to form this we call the oxonium. Oxonium, terbutyl oxonium, positively charged ion. This step is a rapid step. This part is going to be subject to a proton removal. So you call the deprotonation. So in this oxonium, what's going to happen? Your oxygen and hydrogen, that bond is going to be subject to the breakup. So due to the water molecule has oxygen has 2 lone pairs, one of the lone pairs is attracted to your proton. So therefore this proton as a pure proton going to be moving away to the water, so form another hydronium. Therefore your catalyst is going to be recovered, and then this proton oxygen bond break up to form an alcohol. This is how you produce alcohol from hydration of alkene. This hydration and dehydration, as we mentioned, they are going to be in equilibrium. Hydration of alkene is the reverse of your dehydration of your alcohol. So if you have your alkene reacted with water in the strong acid solution, you are going to produce alcohol. Similarly, if you have alcohol adding strong acid as a catalyst, this alcohol may be produced propane. The question is, when they are related to the equilibrium, which one is favorable? Forward reaction or reverse reaction is going to be favorable. How do you determine it? How do you ensure the reaction goes to the direction as you hoped for? How can we ensure the reaction goes in the desired direction? So here we need to recall the Ch6 principle. From your general chemistry study, if your equilibrium is going to be reached, and then you are going to apply an external stress, your equilibrium is going to shift to right or left based on the Ch6 principle. The Ch6 principle states the system at equilibrium adjusts to decrease or minimize any external stress applied to it. In our hydration and dehydration reaction, so your water is your major external stress. Your key stress is your water. Therefore, if you are adding more water, let me do this. You add more water, the reaction want to decrease this water. How do you decrease the water addition? You move your reaction to the forward, meaning you are going to produce more alcohol. If you remove water, you keep removing water, your reaction wants to increase this decrease. Your reaction is going to adjust, your equilibrium is going to adjust to minimize this change. You decrease it, your reaction want to increase it. So therefore your reaction go to the reverse, meaning you are going to have your dehydration. Again, to summarize for this hydration and dehydration. Hydration and dehydration, this system at equilibrium. This equilibrium can be adjusted to minimize any stress applied to this system. And hydration and dehydration equilibrium, in this kind of equilibrium, the water is the key stress. If you add in water, the reaction will be adjusted to produce more alcohol to the forward. If you remove water, the equilibrium will move towards to the reverse direction to produce more alkene. This is about the Ch6 principle. Based on this Ch6 principle, you can also establish the equation with the thermodynamics. Delta G, Gibbs free energy change equals to the Gibbs energy for your product minus Gibbs energy for your reactant. The reaction is going to occur spontaneously. Reaction is a spontaneous one if delta G is smaller than 0. Delta G is negative, reaction will spontaneously occur. There is another possibility for you to evaluate the equilibrium. You also can use equilibrium constant K. Capital K equals to the concentration of your product, the multiplication of concentration of product divided by the multiplication of your concentration of your reactants. If this equilibrium constant is very large, your reaction to the forward is favorable, or forward reaction is complete. Otherwise, if this equilibrium constant K is very small, meaning your reaction is not reacted, or the reverse reaction is your favorable reaction. This is about the addition reactions. So you have 3 different types of addition reaction. We mentioned hydrogenation, hydrohalogenation, hydration. A little later, we are going to study halogenation. You are going to produce a vinyl dihalides. Before that, we are going to show you another hydration reaction, which we are going to follow anti-Markov-Nikov's rule. So you have a hydroboration oxidation of your alkene. This reaction will not follow Markov-Nikov's rule when you add in water to the alkene. What's the chemical reaction? What's the mechanism? Why this is happening? What kind of condition we needed? We are going to discuss it in the following lecture. So we are going to give everybody a break, 5 minutes break, and then we come back to continue your chapter 6, reaction of your alkene. To emphasize, reaction of your alkene can be addition reaction, can be oxidation reaction, can be polymerization reaction. About your addition reaction, you can have totally 5 different types of reactions. I will summarize it for you. Oxidation reaction, you have 2 major ones. You are going to form an epoxidation, another one called ozonolysis. So let's again take a 5 minutes break. We come back, we are going to discussing hydroboration and oxidation reaction of your alkene, which follows anti-Markov-Nikolov rule. So have a good day. We'll come back in 5 minutes. Thank you so very much.